Welcome to ARM DevSummit. Thank you for joining us for today's session, Implementing 3D Neoverse N1, 3D Design Merits Meet In-Depth Analysis. My name is Metcalfe, and I'm the Product Manager for Digital Implementation at Cadence, and I'll be presenting an overview of the Cadence 3D IC solution during this session. We will be taking questions at the end of the presentation. If you have a question, please enter it in the questions and answers box, and we will respond once the presentation finishes as time allows. Our session today is also presented by Shawn. Shawn is a principal design engineer based at ARM Austin, working on IP and chip implementation across a broad range of process cores, system IP, and system on chip to fulfill silicon-proof validation, platform demonstration, and advanced flow exploration on the cutting-edge process nodes driven by best-in-class PPA targets. He has over 18 years of experience in chip implementation and physical design methodologies. Prior to joining ARM in 2012, Shawn had held several positions in companies such as Realtek and a Bay Area startup in a technical lead role, physical design, methodology development, and mixed signal back-end engineering. Over to you, Shawn.
Thank you for your introduction, Rod. So we start from today's agenda. So I will start from to introduce a background, the motivation for this 3D stacking the CPU implementation, and also briefly introduce, provide an overview of this technology trend and the development in recent years. And then we will move forward to the main topic. It will be the implementation flow. The main focus will be on power grid construction and the connect distribution over the 3D layers. And later on, we also provide insights. I think that's the main concern from many users to deploy this technology is a thermal. That's a 3D thermal analysis from this simulation study and the IR analysis. And both analyses are based on the Cadence solution. That's a Voltus Associates. And finally, we will wrap up this presentation by conclusion. So regarding the motivation, why do we have a 3D stacking? Essentially, that's a primary benefit. It's pretty much holistic. It's from, I think, the power and performance perspective. We pretty much get this kind of increase the bandwidth and the lower latency from shown 2D to 3D design. Because we do see that the wire, not just a delay, but also capacitance pretty much reduced, benefited from that's a 2D, that's kind of long 2D connection, very much shorter the vertical 3D connection. And also we could essentially to encapsulate the more computer design, the higher density in the same footprint. So in terms of, I think from a cost perspective, typically it's a highly costly for the IP company to design that's a brand new the hard IP, not only for the I/O, the hard IP on the advanced process node like 7 or 5 nanometer. So this technology, 3D technology, just similar like a chiplet design, provide a kind of more flexibility. We could stack different kind of IP through this kind of 3D stacking. So typically, I think it's quite of based use case in the right side. We have the I/O at the bottom because that's much less essentially that's the least area beneficial from the process scaling. And then we have SRAM, the RAM stacking at the middle tiers. That's kind of 7 nanometer, and they get the most dense and performance, so the most performance compute logic at the top level. That's the most cutting edge 5 nanometer design. So regarding the recent years 3D technology trend, this table essentially is from the iMac, shows the 3D IC roadmap. The different flavors of the 3D are categorized based on the size and the inter-tier VR or TSV. The size also dictates the VR density and hence the design hierarchy at which we can partition. For example, the technology available today is on the far left. with dimensions of TSVs in the 1 to 5 micron range, allowing 4 to 100 years in a given design, and allowing design to be split at a die or block level to make it possible. Whereas if we move forward to have a much more finer pitch in the 100 nanometer size vias, we have what is known as a true or authentic 3D, also called monolithic 3D, in gate and the transistor level. This technology, if we have reached this level of advancement, this technology would allow us to have 2 separate tiers of even in the device level with intermediate interconnect layers connected using much finer pitched vias. So I will show the animation to help the audience delineate the wafer-to-wafer bonding scheme in face-to-face stacking manner. As shown, it's the lower tier, the lower die is on the right side, the upper die is on the left side. And we stack together like this. Yeah. So as shown, it's called face-to-face. That's why it's called face-to-face wafer bonding. Because the wafer bonding layer is here. And in this technology, TSV, essentially that's coming from the backside bump. It represents I/O from backside. So regarding the process details, the bonds are copper. The wafer bonding process, as shown here, is the whole assemble the stacking 3D stacking design like this. So the wafer bonding process is done at a room temperature, and a small amount of liquid is used to create a non-permanent covalent bond to initially stick the wafers together in a very precise fashion. Essentially, this kind of wafer-to-wafer bond package is around 5 micron, whereas so the alignment must be a fraction of this pitch. The liquid was dropped at the center of wafer and sprayed for chemical bonding to stick wafers. The wafer structure is then put in an oven to heat, at which point the ionic bonding occurs and the copper bonds truly and physically attached to each other. So this is what we call the Trishul test chip. That's our very first silicon project to build on this technology. We have reached 5.76 micron. And in the initiative for the 3D folded CPU design in this presentation, we explore the limit down to just 1.8 micron. And it should be kind of feasible in terms of the bleeding edge technology nowadays from the foundry. So Trishul project is on get the first proof point to prove that the readiness of this 3D stacking technology. So it's built based on the GlobalFoundries 12 nanometer FinFET process node, and the design used for this test chip is a CMN600. So CMN600 is a kind of coherent mesh interconnect IP aiming infrastructure application. So actually we just, because it's just a test chip to give a proof point, we don't really build a whole system. We grab like a 2 by 2 mesh topology from this picture as shown here, you see. So we build a kind of 2 cross points at one tier, the other 2 cross points at the other tier. So we rapidly build this design essentially to use to flash the flow, the 3D methodology flows, and we tape out last year and get a silicon back this year, get a very, very promising result. And not just for the high yield as shown, but also we have a measure from the ring oscillator, the 3D ring oscillator in this test chip. We could achieve the gate delay between 3D layers just in very encouraging 10 to 12 picoseconds. Essentially, it's equivalent to 2 fan-out gate in 2D design. In real 2D design, if you if you analyze the flight time from this cross point to this cross point, over hundreds of micron, it also requires hundreds of picoseconds. So it's very encouraging to get to this proof point. And essentially, if we we have a further optimization, we could achieve just down to 6 to 5 picoseconds. And furthermore, someone concerned has worries about the 3D interface parasitics introduced from wafer bonding. It's negligible. even the top 2 layers, typically, that's the most 6 layers we use to build a global power grid supply. So it's this impact is negligible. And also the process skew between the wafers is also manageable. The variation we have seen is pretty minimal. So we don't really need to apply substantial margin to account for this variation. And we have also testing over 334 wafers over 2,000 die. So overall, we have a test over almost 40 million 3D connection. And the operation frequency is also very encouraging to, it's attainable for 2.4 gigahertz at a super overdrive for this CMM test chip design. So CPU implementation. So the motivation, we want to build a 3D microprocessor system. I think from CPU to system level is the growing memory cache capacity is more and more demanding. I think in CPU levels, L2 cache need to increase for performance improvement, but typically it's in the compromise of latency for memory access. And in the system level, typically the hyperscale system with a max core count, L3 memory access, system level cache memory access will be more than crucial for the whole system. And that's why that the CMM or coherent interconnect is the solution to resolve this bottleneck. Essentially that also enable the possibility for L3 cache stacking. And the Trishul is essentially the best practice to get our proof of concept from that 2x2, the matrix topology test vehicle, as shown in previous slide. But at the CPU level, we also want to explore the possibility we could also get the same benefit from the 2D, the 2D size increase. That's why we build the design. It's based on the Neoverse N1 CPU. This Neoverse N1 CPU is our very first flagship level aiming infrastructure application. So this design is essentially based on TSMC 7 nanometer, 7FF. So the 2D is a kind of baseline design, which has a private L1 and L2 cache. So in 3D design, we build a kind of 2 tiers. Essentially, that's a logic over memory here. So the logic is essentially a memory over logic. So memory is in the upper tier, and the logic in the lower tier. It's pretty much to essentially to accommodate the microarchitecture of a Neoverse N1 CPU. Essentially, we use a face-to-face hybrid bonding for less electrical and the power connection between the tiers. So tier 0 memory primarily is a CPU data path, and we put most of all of L1 and L2 cache at the upper tier. And the primary benefit here is we want to achieve a target to reduce 2 cycles, because essentially in the half megabyte L2 cache for the Neoverse N1, that's for 876. 876 is more for the client mobile application. It requires 9 cycles for the half 512 KB L2 cache. Whereas if we increase the cache size to 1 megabyte for infrastructure applications, it requires 2 more cycles in a traditional 2D design, pretty much introduced by wire delay. So in this picture, you can see M4 and the M7 essentially has to be added to 1 cycle per read and write access for the all L2 cache memories. So in 3D designs, we explore the possibility to get the same latency. That means we could also achieve 9 cycles without at least 2 extra cycles in 3D design, and also get a benefit from 2D footprint. You can see there's a kind of smaller for each logic and memory tier, and without a compromise on frequency. Oh, and then I hand off to Rod for introduce a Cadence 3D IP solution.
Thank you very much, Shawn. So Cadence have a comprehensive 3D IC flow, which is represented on this diagram. If we start at the top, you'll see we have the Orbit IO product, This is really there for the chiplet design, because at the start of the process, you need to be able to partition the design the chiplet, do the floor planning. That may be a simple interposer design, or it may be a complete 3D stack. So Orbit.io is there to create the floor plan, create the net list, and it is very heavily connected to the implementation tools that are in the middle section of the diagram. So on the left-hand side, we have Innovus, that's for the digital implementation portion. Then in the middle, we have Virtuoso, which is the full custom implementation platform. And then on the right-hand side, we have Allegro, which is for the packaging and the interposer. So moving from Orbit.io through the flow to implementation, we're able to partition, create the intermediate top-level netlist, do the implementation of the individual parts of the chiplet, and then at the bottom of the diagram, we see the sign-off tools. Now, this is very important. We now need to bring the chiplet back together. We need to do signal integrity analysis. We need to do both IR and thermal analysis. There will be some design for manufacturing checks done probably, as well as the physical design rule checks done in Pegasus. And also, you should consider 3D test. We have the Modus product, which is a design for test product. That also has to consider a 3D stack or an interposer, because you do need to be able to test all these systems once they're fully integrated. So what we see here is a typical Cadence flow. It goes from Orbit.io at the top for the chiplet partitioning and floor planning, through implementation, may that be digital or full custom or package, and then we end with the sign-off tools at the bottom. So moving to the next slide. This really goes through the implementation flow that was used for the Neoverse design. So if we start at the top, Genus was used for RTL synthesis. This is where the whole of the Neoverse design was created, and a netlist was generated for handover to Innovus. At the beginning part of the physical implementation flow, Innovus was used with both tiers, in effect both dies, concurrently held within Innovus, and then the initial placement, the optimization, and the clock tree synthesis was done. After the clock tree synthesis, the design was physically partitioned into two tiers. So now we have die 1 and die 2, and Shawn mentioned the configuration of those. Once we've done die 1 and die 2 routing, the system is then brought back together again, and we then move into the sign-off flow. So Tempus and Quantus were used for extraction and static timing analysis, and then Voltus and Celsius was used for IR drop and thermal analysis. Okay, I'm now going to hand over to Shawn, who's going to go through more of the details on the implementation flow.
Okay, thank you, Ra. Okay, so essentially we start from floor planning. So essentially for a 3D, this kind of 3D 4D design, the main I think the main consideration is we should avoid to have kind of a logic over logic design at least for this 4D CPU, because there's a high switching activity should not overlap in the vertical direction. Essentially, in the later on we'll have a temperature and thermal analysis benchmarking. You will realize that this kind of logic over logic design have a significant penalty on the thermal profile. Yeah. So that's one of the reasons we want to keep a logic and memory as a separate die. And also, we also want to have decrease that's interconnect length for the inter-block connection. That's also why we want to have the RAM, the memory, primarily to place the other die, because we want to minimize that kind of wire across the memory macros. So that's also the reason why we introduced a new methodology. I think it's all developed by ARM. Is called virtual anchor cell insertion. It's introduced to virtually represent the cross-tier pairs and the conceptually align with 3D to enable that cross-tier co-optimization in the placement. So this methodology as shown in the graph, you can see that the anchor cells always come with pairs and conceptually align with 3D. So this anchor cell essentially is based on the minimum size of buffer. It's essentially a hack cell to represent. We have the terminal at the top layers for the routing, essentially to mimic the real routing to the wafer bound layer. So essentially, this kind of cell is virtually exist to essentially to represent the two-tier 3D connection on the left here. So in our 2D representation, anchor cells are conceptually aligned in 3D and connected with dummy wires at top layer, like in this case, it's metal 15, before the global supply grid is distributed at that layer. And then we cut the layer. We cut the dummy layer essentially to snap the signal terminals to the closest assigned micro bump, also you can call it a wafer bound, and remove the virtual anchor buffer pairs, because essentially it's not required after we get that base location of this anchor cell for the cross-tier placement optimization. And then we partition the design. We partition the design essentially as a slide and a flip, so that we could get the realistic 3D connection. Yeah, essentially in our proposed flows, this is done before the routing step. Eventually, you can have the same design as shown at the right side as a kind of cross section. Yeah, so essentially we use a minimal size buffer. It's just a dummy buffer, so that's a delay is just a kind of placeholder to represent this kind of connection in 2D context. It's a modified standard cell views. So in terms of the power grid, I think that the primary focus will be from the backside TSV, that's IO TSV, to the wafer bound. So the most important role, we have to minimize the effective resistance, also kind of IR drop from TSV to die interface. Because in the traditional 2D design, we have the IR drop from the package level, to the top layer and down to the device level. Whereas in 3D stacking design, we have this additional path, or you can say kind of segment, to introduce more the IR drop. So how to minimize IR drop will be like kind of a key focus. We make this 3D stacking design feasible from the IR perspective, the voltage drop perspective. So that's why we propose to build this kind of so-called stack via, or you can say that's a waffle via, to minimize the effective resistance to the die interface, as shown. So I will talk more in the IR analysis section later on. So regarding the card tree construction, the primary concern on 3D card tree is OCV, as always OCV. The OCV on chip variation is pretty restricted, notably this kind of CPU 40 design. It's pretty much restricted by our CPU microarchitecture. Typically, we have a sequential clock gating to save the power and to essentially minimize the OCV at a 2D context. So we have 3 levels of the clock gating: architectural, regional, and the synthesizable local clock gating. So it's really hard for us, to use a traditional mindset to implement the 3D clock tree to mitigate the OCV. So from here, inside, it's in the left side, you can see that's a whole clock route across the tiers. So it's shown in 2D. So it's all the things, including green and brown. So at the right side, all the green things at the lower tier, the brown things at the top tier. And the root is from the bottom die. So this slide, essentially, you can see that the anchor cell pairs introduce insertion to represent the multi-top tier clock route as shown. So you can have the kind of corresponding the pair, it's the lower tier. So we introduced the anchor cell here. Essentially, that's to connect to the top tier before class tree construction. To identify all these points. Yes, as shown, it's this floor plan image layout. Okay, so we start the CTS from bottom tier. Essentially, that's you can see that's the first that's a clock top level. It's a clock tree distribution from bottom root to insert clock buffers, inverters, just in traditional CC after manner. And then we build a trunk. That's from top level and then the trunk level, but still limited at the bottom tier. And then we connect the anchor cell, reflecting the corresponding top tier clock roots as shown, and the sinks specifically at the bottom tier. So let's say we get all the bottom tier clock tree connected, including both these anchor cells and the sinks at the bottom tier. And then finally, we connect the rest of the sinks from the anchor buffer roots at the top tier to finish the whole clock tree distribution through the 3D. And then the motivation, the advantage is essentially to move all these cross-tier clock divergence to the downstream clock tree level. Essentially, it's much closer to the sinks, essentially to mitigate the inter-tier OCD, as shown. So the benefit we have seen, we could have this kind of analysis matrix here. So not only that the power is pretty much decreased. You can see that the dry storm mass power we could decrease over 20 to 30 picoseconds. And due to the significant tree capacitance decrease, we could also gain pretty benefit from the power scaling here. It's down almost 30% off. And much less clock buffer inserted, and also over almost 20% clock latency improvement. Okay, so regarding the thermal analysis, this is our initial takeaway from the Celsius-based analysis. The 3D effects for the 3D stacking is, as always, these are the main concern. And this heat map indicates the hotspots are always on logic for the given representative workload. In this case, we apply mass power. The reason why we apply mass power is a viral vector. It's useful for the stress test, essentially to magnify the temperature increase from this thermal impact introduced from 3D stacking. As shown here, you can see that the green, that's this comparison. The green one, that's the green is refers to mass power. The orange refers to dry cell. So as expected, the mass power is a power viral vector. We can see a much more noticeable increased temperature comparing to dry stone. So our observation is a logical over memory is the best beneficial for heat dissipation, as the heat sinks are essentially on the top. But unfortunately, it's not practically viable from microarchitecture perspective. Essentially, it's also somehow applied to face-to-face versus face-to-back comparison. Even though in the face-to-face, we have a device, device closer to the top, so also closer to the heat sinks. And the CPU on CPU is always the worst option, as a unit with high switching activity should not overlap in the vertical direction. 3D IR analysis, the main challenge we need to tackle is, as introduced aforementioned, it's essentially introduced from the backside bump, backside TSV to the die interface micro bump. So the effective R must be effectively mitigated. So the initial IR drop result also prove our expectation. So as shown here, you can see 4.1% drop introduced from that's from this via pillar from the backside TSV to die interface. And essentially, that's the local grid accounts for 2.1% only. So overall, the cumulative is around 6%. So about 2/3 of IR drop contributed from this stacked waffle via. So I think that's how to optimize this kind of waffle via, and also to effectively increase that's a TSV, and without the significant impact on PPA will be our, I think the primary focus to explore the feasibility of a 3D folded CPU implementation. Okay, so finally, my conclusion. Essentially, this is a very promising result we gained through the implementation to analysis based on Cadence solution. And we also get a proof point that this kind of logic over memory partition, we could achieve 2-cycle lower L2 access than 2D. So it's a significant benefit. We see the value of that 3D stack design, at least from L2 level. And furthermore, I think the same methodology is also applicable for the system level design to reduce the cycle and access time for the L3 cache. So this RTO to sign-off total solution based on Cadence digital flow gives us a kind of comparable frequency with significant area and the power benefit versus 2D design. And this CTS demonstrates 3D CTS is the clock latency, the clock buffer count, and the power is also considerably reduced. And the primary challenge will be 3D power delivery network. We still see that to a 6.2% IR drop is not that encouraging. So our next step is aims to have a further optimization on the via pillars stacked from the TSV. So we aim to further reduce the impact to minimize the PPA. Whereas if we have a more source from TSV, from backside, it will be pretty much improved, this result. And the thermal analysis, we see essentially it's even based on that 2D, based on the mass power viral vector, it's just a 6 degree higher than 2D. So this makes this 3D stacking technology with the heat sinks is a much more, give us a kind of confidence on the feasibility of a 3D stacking from the thermal profile perspective. Whereas some advanced cooling techniques would be essential and crucial to apply for the heat sinks to mitigate the impact introduced from 3D stacking. And also, that's a memory data from the Trishul test chip give us a very solid proof of point to prove this 3D stacking technology viable and ready for production. Okay, thanks for your valuable time, and we prepare to have a Q&A session. Thank you.